Alright, this is another video where we're going to work through Griffith's quantum mechanics section by section. And this is 1.5, which is talking about momentum and operators in general. So to start, we say the expectation value of our position is the integral from negative infinity to positive infinity x times, and this is the modulus of psi squared dx. Okay, so real quick, before we get into some of this, I want to talk about what this actually means, because there's very common misconceptions here. The first problem is when we say expectation value, and I talked about this in the probability video, expectation value is not the same as the value you're expecting to see. It's an average. But an average of what? So this misconception comes from, if you can imagine, let's see if I can get this up, a box, and inside this box you have a particle, and let's say you observe the particle to be at position C. And then you think, okay, now maybe I look away, I do something, and then I come back and I measure it again. And maybe it's in a different position, D. And you keep doing that and then average that out, and that would be your expectation value. The problem with this is, if you remember in section 1.2, once you observe the particle, the wave function, we say, collapses at whatever position it's seen at. So you're not going to get another measurement of D. So instead what we're doing is, imagine you have the exact same box and the exact same wave function that describes this particle, and you measure it in, maybe now it's in D. Okay. And if you have another box, and again you have the same state, you'll measure it in a different position, and you can keep doing this and doing this, at least in theory. The average of that is your expectation value. Okay? So that's what that is. Now let's get into the math a little bit. We're going to define the expectation value of your velocity to be the time derivative of the expectation value of your position. So if we go to our definition here, if we take a time derivative of this, we'll be able to get our expectation value of velocity. So similar with classical mechanics, if you solve your equations of motion, be it Newton's law or Lagrangian or Hamiltonian's, and you get an equation of motion, you can very easily, by just taking a derivative, a time derivative, get your velocity. So that's all we're doing here. This is kind of the analog to that. Okay, so this will be the derivative with respect to time of the integral of x and the square of our wave function. Now, a lot of this is going to be similar to the math we did in the last section with normalization, and showing that your normalization constant is constant in time. It is a constant. We can do the same trick by moving our derivative inside the integral and making it a partial derivative. And because it's a derivative with respect to time, our x value we can actually move over here. This would be the integral of x d by dt psi squared dx. Okay. Now this we actually did in the last section. So if you want to know what this is, if you just flip over to the other page on equation 1.22, it works through that, and if you're confused by it, I did it in the last video, so you might want to check that out. But just to save us some time, our expectation value can now be I h bar over 2m, the integral of x d by dx psi star d psi by dx minus d psi star dx times psi dx. And now what we want to do is integrate this by parts. Now I want to mention for a second, because this could be a little confusing. If you remember integration by parts from, say, Calculus 2, at least I remember being given this sort of acronym that helps you decide what should be u and what should be dv. I don't remember that, but I think the better method is let whatever is easier work. So again, integration by parts, uv minus the integral of v du. Okay. So in this case, we could let u equal x, so that du is dx, and then dv we can let be everything else here. And then when we integrate this with respect to x, this is just from the fundamental theorem of calculus. We'll just get our inside part here. Okay. Now we're going to do the integral of uv minus the integral of v du. But v has our wave function in it, and remember that our wave function is normalizable. So when we evaluate this from negative infinity to positive infinity, this should go to 0, because our wave function has to go to 0 at those bounds. Okay, so then we can simplify this a little bit as minus our constant terms out here, I h bar over 2m, the integral of v, which is all of this, times du. So we're just going to put all this in this new integral. And now this is equation 1.30. And this integral can be distributed, but the part we're interested in is this second one. So I'm going to do this over here. The negative side can come out, so that's I h bar over 2m. We're not really worried about that, but the integral from negative infinity to positive infinity of d psi star dx psi dx. Now again, we're going to use integration by parts, and we'll let u equal psi and then du will of course be dx, d psi dx. And then if we let dv be, this should work out the way that we want it to, dx. Then if we integrate this, our v should just be psi star. Okay. So again, uv minus the integral of v du. Once again, uv goes to 0 from our bounds. Because our wave function is normalizable, they go to 0 there. So we're left with just minus the integral of v psi star times right here. But you'll notice that is exactly this term here. So essentially, and we have a negative sign, so it makes it positive. So essentially, when we add those together, you're going to have a 2 psi star d psi dx. And then we'll pull this 2 out to cancel with this 2 here. So then we get minus I h bar over m, the integral of psi star d psi dx dx. Alright, so now we have velocity, and this is analogous to our velocity in classical mechanics, but a little bit different, and we'll talk more about that later. But at least for right now, I want to be comfortable with our operators and what they're doing, and then we'll get more into, I guess, their meaning. Now, our momentum is mass times velocity, at least classically. So our expectation value of momentum is m times d expectation value of x with respect to time. So it cancels our m. And now we have our expectation value of momentum. Now the ones we're mostly, we usually don't use our velocity expectation value, it's usually our momentum. And one way you could write them is expectation value of x equals the integral of psi star x psi dx. So this is somewhat of an operator. In this case, x, the operator of x is just x, so it doesn't really matter, but with momentum it actually will. So in our box here we'll have minus I h bar d by dx. This would be the full wave function, psi dx. So this, you can kind of see why we call it an operator, because it's operating on the wave function to the right. That's why when we squish our operators between our wave functions, it's important that we do that. In the case of x, it doesn't really matter. Multiplication's commutative, so that is fine, and it's not defined in terms of a derivative. But with your momentum operator, it becomes very important because your derivative has to operate on your wave function, not the complex conjugate of it. So that's important to know. You can definitely make mistakes from that. And from this, we can kind of get whatever else we need. So kinetic energy is equal to your momentum squared over 2m, again, classically. Your angular momentum is your position vector crossed with your momentum vector. Right? So we can define both of these values through our operators, in this case p, but x as well. And any operator can be defined in terms of x and p. And this is kind of our general way of doing it. And I'll explain what this means, because it's a little weird, but I think it makes sense. Basically, all that this is saying is if you have some dynamical quantity in terms of the position and momentum, all that you're doing is replacing your position with x, which is not a big deal, and your momentum with minus I h bar d by dx. So, for example, if you wanted to calculate the expectation value of kinetic energy, that would be minus h bar squared over 2m, the integral of psi star times the second derivative of psi with respect to x dx. So all that we do here, we have our 2m that we pull out, I h bar squared, so p squared, instead of p, we do p squared. So you'll have I squared, so that's where the negative comes from, h bar squared, that's why that's squared, and then we're taking not the first derivative, but the second derivative of our psi, because our p is squared. And I know that seems a little weird because like this isn't an exponent, but just know that with operators it works out okay. Maybe that's something we can show later. That was something that confused me at first, but it does work out that way. Okay, and that is all of 1.5. I'm going to do maybe a problem on this and then move on to the uncertainty principle. So if you're enjoying these type of videos, please like and subscribe, and I'll keep posting more. Thank you.